Look up at the night sky on a clear night, and you will see stars. Thousands of them, scattered everywhere, glittering like tiny lights on a black canvas. It feels random, like someone just threw a handful of glitter into the air and walked away. But here is the thing, it is not random at all. If you could zoom out far enough that entire galaxies looked like tiny dots, far enough that millions of light years felt like inches, you would see something that would stop you cold. You would see a web, a giant cosmic web stretching across the entire observable universe, made of galaxies, gas, and invisible dark matter, all connected in a pattern so enormous and so beautiful that it took humanity most of the 20th century just to realize it was there. That web is what this video is about, not just what it looks like, but how it works, how it formed, what the biggest pieces of it are, and what is eventually going to happen to all of it. By the time we are done, the universe is never going to feel the same to you again. So let us start with the most basic question. What actually is this cosmic web, and what is it made of? Scientists break the cosmic web into 4 main parts. The best way to picture it is to think of a giant marine sponge sitting in the ocean. The solid material of the sponge, the stuff you can actually touch and squeeze, represents 3 of the 4 parts. The open holes running through the sponge, the empty channels where water flows but nothing solid lives, those represent the 4th part. Now, let us give each piece its proper name. The first part is called nodes. These are the dense, crowded intersection points of the web. Physically, nodes are massive galaxy clusters and superclusters, regions where gravity has pulled so much matter together. In the sponge picture, nodes are the thickest, densest clumps of solid material where multiple strands all meet at once. The second part is called filaments. These are long, thread-like channels of dark matter and gas. Filaments are the highways of the cosmic web, the roads that matter travels along as it flows from one dense region to another. A single filament can be anywhere from 160 million to 260 million light-years long. The third part is called walls or sheets. These are flat, two-dimensional membranes of matter. They act like ramps that funnel matter inward toward the filaments and eventually toward the nodes. The fourth and final part is called voids. These are the enormous, mostly empty bubbles that dominate the universe. A typical void can be anywhere from 98 million to nearly 1 billion light-years across. In the sponge picture, voids are those open holes running through the middle, the spaces where almost nothing lives. Now, here is something genuinely surprising. Voids take up about 76% of all the space, while containing only about 10 to 15% of all the mass. Filaments take up about 6% of the volume. Walls take up roughly 18%, and the incredibly dense nodes occupy only about 0.02% of all space. Almost nothing by volume, but absolutely packed with matter. It is a continuously flowing, evolving network, and where you draw the lines between its parts depends on the tools you use to look at it. So, how did we figure out any of this was even there? For most of human history, we had no idea the cosmic web existed. Galaxies looked scattered and random through early telescopes. The first real crack in that picture came in 1978, when 2 astronomers named Stephen Gregory and Laird Thompson looked carefully at the region around a giant galaxy cluster called the Coma cluster. What they found was not just a cluster sitting alone. They found a physical bridge of galaxies connecting Coma to Able 1367. For the first time, someone had evidence that galaxy clusters were not isolated islands. They were connected to each other. 2 astronomers at the Harvard-Smithsonian Center for Astrophysics, Margaret Geller and John Huchra, had spent years patiently measuring the redshifts of thousands of galaxies in narrow slices of the sky. Redshift is the key tool here. When a galaxy is moving away from us, the light it sends gets stretched toward the red end of the spectrum. Since the universe is expanding, the farther away a galaxy is, the faster it appears to move. Redshift is basically a cosmic ruler. When Geller and Huchra plotted their galaxies, they produced the Stickman map, one of the most famous images in astronomy. The real shock was the CFA2 Great Wall, a continuous snaking filament stretching across the map. This wall stretched at least 500 million light-years in length, yet was only about 16 million light-years thick. Reflecting on what the map revealed, Margaret Geller said, "The universe appears to have a bubble structure, with galaxies on the surfaces of the bubbles and nothing in between." That one sentence completely changed how astronomers thought about the large-scale universe. In the years that followed, bigger surveys like the Sloan Digital Sky Survey mapped millions of galaxies across the sky. These surveys revealed the cosmic web in stunning three-dimensional detail, looking remarkably like that cosmic sponge. When astronomers added up all the ordinary matter they could detect in stars, cold gas clouds, and galaxy clusters, the total kept coming up short. This became known as the missing baryon problem, and it bothered cosmologists for decades. The answer was hiding in the filaments, an enormous reservoir of gas called the Warm-Hot Intergalactic Medium, or WHIM. In 2019, teams detected this gas by stacking signals from hundreds of thousands of galaxy pairs. It was the missing link. Everything you just heard about started as something smaller than a single atom, unimaginably smaller. In the first fraction of a second after the Big Bang, the universe went through a period called cosmic inflation. Imagine taking something smaller than a proton and blowing it up until it is larger than a grapefruit. That happened almost instantly. This expansion was driven by the inflaton field, which had tiny, random quantum fluctuations built into it. Imagine a balloon with microscopic wrinkles. Inflate it to the size of a planet, and those wrinkles become visible mountains. Inflation took wrinkles at the quantum scale and stretched them into the seeds of everything, the foundations of the cosmic web. About 380,000 years after the Big Bang, the universe cooled down enough to become transparent. This is recombination. Photons were suddenly free to travel. We detect them today as the cosmic microwave background radiation, the oldest light in the universe. In 1992, George Smoot and John Mather detected these faint temperature differences. Stephen Hawking called it the discovery of the century. Dark matter began clumping first, building the invisible scaffolding of the web, while ordinary matter was still locked in plasma. The early universe was filled with a plasma that could carry sound waves. When a localized overdensity formed, it sent out a spherical pressure wave, a pulse of sound radiating outward at roughly 60% of the speed of light. This wave pushed both dark matter and ordinary matter outward from the center. At the moment of recombination, the plasma disappeared and the sound speed dropped almost to zero, freezing the wave permanently in place. In 2005, Daniel Eisenstein and his team detected this frozen fingerprint in the positions of nearly 47,000 galaxies from the Sloan Digital Sky Survey, finding the predicted bump in the statistics at exactly the right separation scale. Those ancient sound waves are still speaking to us today through the positions of galaxies billions of light years away. Think of the biggest thing you can imagine: a mountain, an ocean, a continent, the entire Earth. The solar system, the Milky Way galaxy, 100,000 light years across and containing hundreds of billions of stars. Now set all of that aside completely, because what we are about to talk about makes every single one of those things look like a speck of dust. We are talking about the largest structures ever identified in the observable universe, things so enormous that even the word enormous stops being useful. We are talking about superclusters, great walls, and the staggering emptiness of cosmic voids. Let us start with superclusters. For a long time, astronomers defined a supercluster simply as a large, dense region where many galaxy clusters happen to be concentrated near each other. It was a purely statistical definition based on counting galaxies in a given volume of space. That definition worked well enough as a starting point, but it had a deep problem. It said nothing about whether these structures were actually physically connected, or actually behaving as a gravitational system together. They might just be a coincidental crowd, galaxies happening to be near each other without any real physical relationship. In 2014, a team led by R. Brent Tully at the University of Hawaii introduced a completely new and physically meaningful definition. Instead of just counting galaxies, they mapped the peculiar velocities of thousands of galaxies across a large region of space. Peculiar velocity is the motion a galaxy has on top of the general expansion of the universe. If you subtract out the background expansion, what remains tells you which direction a galaxy is being pulled by gravity. If you subtract out the background expansion, what remains tells you which direction a galaxy is being pulled by gravity. Tully's team traced these velocity flows and found that the universe naturally divides into distinct basins of attraction. A watershed is a perfect way to picture this. On Earth, every raindrop that falls within a given watershed will eventually flow through the same river system. Tully's team found that galaxy peculiar velocities work exactly the same way. Across a region spanning 520 million light-years, every galaxy's motion flows toward a single central basin. They named it Laniakea, a Hawaiian word meaning immense heaven, chosen to honor the Polynesian navigators who used the stars to guide themselves across the Pacific. Laniakea is our home supercluster. It contains the Milky Way, the Local Group, the Virgo cluster, and approximately 100,000 other galaxies. It spans roughly 520 million light-years across and contains a total mass of about 100 quadrillion times the mass of our Sun. Before this work, astronomers thought the Milky Way belonged to the Virgo supercluster. Now it is clear that Virgo is merely a small tendril of the far grander Laniakea. The gravitational center toward which all of Laniakea flows is a region called the Great Attractor, located roughly 150 to 250 million light-years away from the Milky Way. We cannot see it directly because a thick band of dust and stars in our own galaxy blocks the view, but its gravitational pull is measurable through the motions of thousands of galaxies. Everything in Laniakea, including the Milky Way, is being drawn toward it at hundreds of kilometers per second. It is worth noting, however, that Laniakea as a whole is probably not gravitationally bound. Dark energy, the force driving the accelerating expansion of space, is strong enough on these enormous scales that the watershed boundaries defining Laniakea today will eventually dissolve as expansion overcomes the gravitational flows. Laniakea is a real and physically meaningful structure right now, but it is a temporary one. Beyond Laniakea lies the Shapley supercluster, sitting about 650 million light-years away. The Shapley supercluster is so massive that it exerts a gravitational pull strong enough to affect the motion of Laniakea as an entire system, tugging our whole home supercluster in its direction like a slow cosmic tide. Now let us talk about the Great Walls, which are the largest individual structural features mapped in galaxy surveys. The CFA-2 Great Wall, discovered by Geller and Hucre in 1989, stretches at least 500 million light-years. The Sloan Great Wall, discovered in 2003 and analyzed by J. Richard Gott and colleagues, stretches about 1.37 billion light-years, nearly 3 times longer. But both of those are completely dwarfed by the most controversial cosmic structure ever reported. The Hercules Corona Borealis Great Wall, identified in 2014 by Istvan Horvath and collaborators, is estimated to stretch approximately 10 billion light-years across its longest dimension. The observable universe itself is about 93 billion light-years in diameter, which means this single structure potentially spans more than 10% of the entire observable universe. This is controversial because it violates a foundational principle. The Standard Model predicts the universe should appear smooth and uniform above a scale of about 1 billion light-years. Now, let us move to the exact opposite of these dense structures. Cosmic voids are the vast, underdense bubbles that dominate the volume of the universe. They are surrounded by the walls and filaments of the cosmic web, but inside them there is almost nothing at all. The first discovered was the Bode's Void. If the Milky Way sat in its center, we would not have known there were other galaxies until the 1960s. The surrounding universe would have been too far and faint. Picture the Bode's Void as a single, enormous, completely silent room inside a densely packed, bustling skyscraper. The rest of the building is full of noise, activity, and people everywhere. But step inside this one room, and there is just profound silence and empty space in every direction. Even larger is the KBC Void, also called the Local Hole, proposed in 2013 by Ryan Keenan, Amy Barger, and Lennox Cowie at the University of Hawaii. Their analysis suggested that the Milky Way itself sits inside a giant underdense region spanning roughly 2 billion light-years across, with a local density about 46% below the cosmic average. This means the region of space immediately surrounding our galaxy contains significantly less matter than a typical region of the universe. The KBC void may be connected to one of the biggest unsolved problems, the Hubble tension. Two different ways of measuring the expansion rate give two different, conflicting results. Sitting inside a large underdense void means the local expansion rate is naturally boosted compared to the global average because matter is being gravitationally attracted toward the denser surrounding boundaries, leaving the void interior expanding slightly faster. If the KBC void is large and deep enough, it could account for part of this discrepancy without requiring any completely exotic new physics. There is also the Eridanus supervoid, a large underdense region that has been proposed as the physical cause of a strange cold patch in the cosmic microwave background sky. This CMB cold spot is an unusually large and unusually cold region that is difficult to explain within the standard model. One idea is that photons traveling through the Eridanus supervoid lose energy due to the accelerating expansion of the void interior, arriving at our detectors slightly cooler than expected. A far more exotic alternative suggests the cold spot might be a scar left by a collision between our universe and another bubble universe during the earliest moments of inflation. That idea remains highly speculative, but it illustrates just how strange the implications of these large voids can be. Despite their emptiness, cosmic voids are not completely dead. They host a rare population of void galaxies, isolated systems that have evolved entirely alone, far from the crowded clusters and busy filaments where most galaxies live. A void galaxy is like a lonely farmhouse sitting in the middle of a vast, uninhabited desert, growing and developing in complete isolation, never disturbed by the chaos of the cities. Because void galaxies never experience violent mergers, the stripping of gas by nearby clusters, or the tidal forces of neighboring systems, they tend to be smaller, bluer, richer in pristine gas, and far less chemically enriched than galaxies living in dense environments. They are essentially preserved in an earlier stage of evolution, quietly forming stars at a slow and steady rate, undisturbed by everything happening in the rest of the universe around them. Here is a question that sounds simple, but is genuinely one of the hardest problems in all of science. How do you study something bigger than anything that has ever existed? How do you run experiments on the universe itself? You cannot put a supercluster in a laboratory. You cannot rewind the Big Bang and run it again with slightly different settings to see what changes. So what do cosmologists actually do? The answer comes from two directions working together. One is observation, building bigger and more powerful instruments to map the real universe in finer detail than ever before. The other is simulation, building a virtual universe inside a computer and then checking whether the virtual universe matches what we actually see in the sky. When simulation and observation agree, it builds confidence that the underlying physics is correct. When they disagree, it signals that something important is missing from our models. This back and forth between the virtual and the real is the engine that has driven modern cosmology forward for the past 3 decades. Let us start with simulation. When astrophysicists simulate the cosmic web, they fill a virtual cube of space with billions of particles representing dark matter and gas. Each particle carries a position, a velocity, and a mass. The simulation then uses the laws of gravity to calculate how all those particles pull on each other, moves them slightly forward in time, recalculates all the forces, moves them again, and repeats this process millions of times, stepping through billions of years of cosmic history in a matter of weeks on a powerful supercomputer. What emerges, if the physics is right, should be a virtual universe that looks statistically identical to the real one. The simulation that set the gold standard for an entire generation of cosmologists was the Millennium Simulation, completed in 2005 by Volker Springel and a large international team at the Max Planck Institute for Astrophysics. It tracked over 10 billion dark matter particles inside a virtual cube of space spanning 1.6 billion light-years on each side, running on a supercomputer for weeks. When the simulation finished and the team examined the three-dimensional structure that had grown from the initial conditions, they saw filaments, voids, galaxy clusters, and walls that looked strikingly like the real cosmic web mapped by galaxy surveys. Springel described it by saying, "The simulation demonstrated how simple physical laws acting on the seeds of the Big Bang could grow into the complex, beautiful web of galaxies we observe today." Over the years that followed, simulations grew far more sophisticated. The illustrious TNG project, introduced in 2018 by Annalisa Pilipich and colleagues, went beyond tracking just dark matter and incorporated the full complexity of gas physics, star formation, supernova explosions, and the powerful feedback of supermassive black holes at the centers of galaxies. The Eagle project, led by Jup Shea and his team at Leiden University, developed an independent approach using carefully calibrated gas physics to produce a virtual universe whose galaxy population matched real observations with impressive accuracy. Both of these projects showed that to reproduce the real cosmic web correctly, simulations need to model not just gravity, but all the messy, complicated physics that ordinary matter experiences as it falls into dark matter halos and forms galaxies. The most powerful simulation suite available today is Flamingo, released in 2023 and designed by Jup Shea and an international collaboration. Flamingo models volumes of space spanning billions of light years, tracking dark matter, gas, stars, supermassive black holes, and even the effects of massive neutrinos simultaneously. It requires petabytes of storage and millions of hours of computing time running on one of the most powerful supercomputers in Europe. Shea described the goal by saying, "These simulations allow us to follow the growth of cosmic structure across vast regions of space while still modeling the complex physics of galaxy formation." Flamingo is not just an academic exercise. Its predictions are being directly compared to data from the next generation of major surveys that are mapping the real universe right now. To actually check whether simulations match reality, cosmologists rely on statistical tools that measure the structure of galaxy distributions across different scales. One of the most important is called the two-point correlation function. The basic idea is straightforward. Take a large sample of galaxies from either a real survey or a simulation. For every possible pair of galaxies, measure the distance between them. Count how many pairs exist at each separation distance, and compare that count to what you would expect if galaxies were scattered completely at random. If galaxies cluster together more than random chance would predict, the function rises at small separations. The shape of this function across a range of scales tells cosmologists an enormous amount about how matter is distributed and how gravity has organized the universe over time. When the results from illustrious TNG and Flamingo are compared to galaxy surveys, the agreement is impressive, validating the core physics built into those simulations. This validation is now being extended to unprecedented scales by a golden age of cosmological surveys unfolding right now. The Dark Energy Spectroscopic Instrument, which began operations in 2019, uses a robotic spectrograph with 5,000 individual fiber optic cables mounted on a telescope in Arizona to measure the redshifts of nearly 50 million galaxies and quasars across a huge footprint of sky. Its 2024 results, drawing on over 5.7 million galaxies, already represent the most precise measurements ever made of how the universe has expanded over the past 11 billion years, providing extraordinary constraints on the nature of dark energy. The Euclid Space Telescope, launched by the European Space Agency in 2023, is mapping the shapes and positions of billions of galaxies across 1/3 of the entire sky. From its vantage point above Earth's atmosphere, Euclid measures the tiny distortions in galaxy shapes caused by gravitational lensing, where the gravity of intervening dark matter bends light and subtly stretches the apparent shapes of background galaxies. By stacking these distortions across billions of galaxy images, Euclid is reconstructing a three-dimensional map of the invisible dark matter scaffold of the cosmic web stretching across billions of light years. The Vera C. Rubin Observatory and the James Webb Space Telescope are catching the first galaxies as they assembled, allowing us to watch the cosmic web building itself. In the radio sky, the Square Kilometre Array, currently under construction in South Africa and Australia, will map the faint radio emission of neutral hydrogen gas across enormous volumes of space, tracing the raw fuel of galaxy formation through the web all the way back to the epoch when the first stars were lighting up. One of the most remarkable recent achievements in this entire field was the first direct imaging of the cosmic web's gaseous filaments themselves, not the galaxies sitting within the filaments, but the actual diffuse intergalactic gas of the web. In 2019, Ryosuke Umehata and his team at the University of Tokyo pointed the Muse instrument on the European Southern Observatory's Very Large Telescope at a proto-cluster of galaxies 12 billion light-years away. What they found was extraordinary. Surrounding the galaxies was a network of faintly glowing filaments of hydrogen gas, lit up by the intense ultraviolet radiation pouring out of the galaxies and supermassive black holes within the proto-cluster. These gaseous filaments stretched across about 3 million light-years, directly connecting and visibly feeding the young galaxies at the nodes of the web. It was the first time anyone had directly seen the raw material of the cosmic web flowing along its own threads, transforming theory into something that could actually be observed and photographed. The fate of the cosmic web is determined by dark energy. As dark energy drives the accelerating expansion of space, the filaments of the web will gradually stretch thinner and fade. Gas within them will either fall inward into the dense clusters at the nodes or be dispersed by the expanding space into the growing voids. The walls and sheets that currently bound the voids will thin out and dissolve. Cosmic voids will grow larger and larger, eventually dominating essentially all of the available volume of the universe. The walls and sheets that currently bound the voids will thin out and dissolve. Cosmic voids will grow larger and larger, eventually dominating essentially all of the available volume of the universe. The massive, gravitationally bound galaxy clusters at the nodes of the web will survive the longest. Held together by their own gravity, they will resist the expansion and persist as isolated cosmic islands, increasingly cut off from one another by the vast emptiness growing between them. The connections between clusters, the filaments and walls that make the web a web, will stretch beyond recognition and vanish. About 100 billion years from now, the expansion of space will have carried all galaxies beyond our local group past our cosmic horizon. Their light, stretched to infinite wavelengths by the expansion, will become permanently undetectable. The future Milky Way will look out into a universe that appears to contain nothing at all. No distant galaxies, no filaments, no great walls, just an enormous, cold, dark, and silent expanse stretching in every direction, with no observable evidence that any of the magnificent structure we have spent this entire video exploring ever existed. It is a humbling picture, but here is the perspective to carry away from all of this. The entire observable universe, all 93 billion light-years of it, with all its filaments and superclusters and voids and great walls, is just the small patch of the cosmic web that happens to fall within the reach of our instruments. The full extent of the web, stretching across the regions of space, lying beyond our observable horizon, is something we cannot directly see and may never be able to measure. In that context, the 93 billion light-year sphere we call home is something like a single grain of sand sitting on an endless beach. The beach stretches on in every direction, far beyond anything we could ever walk to. We are fortunate enough to be sitting on one grain of it, and we are just barely beginning to understand the small patch of sand directly beneath our feet.